But, as I mentioned already, running close collaboration with experimentalists, specifically with Uwe Kaiser, a microscopist, University of Ulm, with Florian Manafort, University of Strasbourg, Alice Kalusuinaga from Advanced Science and Technology, which is, by the way, just across the road from Leaders Institute in Tsukuba, in Japan, and with some other people, including Dmitry. So, once more, I'm a theorist, do calculations, and do our research in close collaboration with many microscopy groups. In the outline of my talk, let me start with a short introduction into low-dimensional materials, specifically 2D materials, and defects in these systems. Then I move on to responsive transition metal dichalcogenides to neutron radiation, like molybdenum disulfide, what Dmitry already touched upon. And then I dwell upon defects and impurities in the Tibet and also in some other similar materials. As an ultimate limit of impurities, I'll touch upon two-dimensional random alloys, quite interesting topic in my opinion. And then a little bit about optical electronic properties of dichalcogenides from advanced first principle calculations. And then about two-dimensional silica, SiO2, very interesting structure. And finally, maybe some extra stuff if time allows about defects in truly one-dimensional systems. Actually, just chains of atoms. It's a little bit like off topic, doesn't fit well into my story today, but results are quite interesting. We just like two papers we just accept, one in Nature Materials, one in ACS Nano, and in general, just maybe sneak preview of these results. So I'm coming from Aalto University. I have it already for about 14 years in Finland. And actually it used to be Helsinki University of Technology. It's a bit dark, but you can see this quite nice building. This amphitheater type building built up by Angvar Aalto, who is quite famous Finnish architect. It's a middle-sized university with very strong material science department of applied physics to be precise. Both theorists and experimentalists there. So once more, by doing calculations at different levels of sophistication, I would like to remind you that it's like doing calculations always interplay between accuracy and gravitational power. Here's, by the way, just an example, what you can get from DFT. Nice example of Peier's distortion when you remove atom from graphene. You have basically a single weakness, how it reconstructs, you can see here. Basically, a physical example of Peier distortion. A lowering of energy by breaking up the original symmetry of the crystal lake. Just an example of what you can do there. So, but today I'm mostly presenting results of density functional theory calculations, which is our workhorse, and not that much of empirical potential, analytical potential molecular dynamics. First, maybe brief introduction into 2D systems, as I don't have to talk about graphene and why graphene is exciting and why graphene stimulates so much research on 2D systems. Actually, we have been collaborating with Andres Gaim group. We published two papers together, actually focused on defect-induced paramagnetism in graphene. But today, again, I'm not going to talk much about graphene, mostly on dichalcogenides. So as we know, Costa and Andre were rewarded by the prize in their discovery, and a group family of other 2D materials were found, basically synthesized or created by different techniques later on. And among them, transition metal dichalcogenides. You basically take chalcogen atoms, sulfur, selenium, tellurium, and mix up them with transition metals and get basically any material you want, more or less, from the point of electronic properties. You can have a metal, you can have semiconductor, you may have charge density with insulator. This and graphene is boring, and dichalcogenides are much more exciting, at least from the point of theorists. They can also exist not only single layers, what you can see here, it actually consists of 3 layers of atoms here. Yellow atoms are sulfur, the green ones are molybdenum atoms, and we can stack them like complete analogy, graphene and graphite. As I mentioned already, they may have different electronic properties. Only disulfide has a gap, which is quite important from the point of electronics. The gap is direct, photoluminescence and other, let's say, related applications in optoelectronics. And the general mechanical properties are also very nice, high mobility, electron mobility, I mean. So, in general, lots of interest now in these systems. And all these systems, basically 2D systems, not only 2D systems, but also 3D systems, bulk material have defects. Thermodynamics gives rise to formation of defects, simply basically gain in free energy. When you mix up, basically create some defects in the system at finite temperatures. Besides, many 2D materials are man-made. So, as, for example, CVD grown, chemical vapor deposition grown graphene is man-made, or dichalcogenides, and contrary to normal, I mean, for example, Scotch tape, graphene you get by peeling the layers from graphite. Mother Nature didn't have millions of years to equilibrate your structure. So it may not be in equilibrium, and you may have some defects, which basically point defects, which may appear at the growth stage. You didn't have enough time to annihilate. Besides, defects can be created artificially. We all know that, for example, ion beam implantation is the heart of semiconductor technology. Defects may be useful, and specifically irradiation-induced defects. To this end, prior to proceeding to really the dichalcogenides, I would like to mention that we have worked for many years on the radiation defects in graphene. Just recent papers published in collaboration with several experimental groups. Specifically, recently we looked at response of graphene on metal substrates to ion radiation. Basically, this is something that happens when xenon ion hits graphene on metal substrate, basically on the grazing trajectory. And this is the top view, what you get in calculations, and this is what you have in experiments. So ion beam comes from the left. Pretty much the same holes as you can see here, and then if you heat up the system later on, necklaces will migrate and coalesce, and this way you can make a nano mesh. Very interesting, actually, results and potential applications in nanoelectronics, the way how you can open a gap in graphene. Okay, but let's move on transition metal dichalcogenides. As Dmitry mentioned already, these materials are routinely characterized using transmission electron microscope. This is again single sheet, and energetic electrons go through your tongue. The first thing, student, when you start learning quantum mechanics, the first thing you learn is the dualism of electrons. Basically, it's particle wave dualism. On the one hand, electron is a wave, it's how you get the image. On the other hand, electron is a particle. It has energy. It can knock out atoms from your target and create defects. For example, this is a Morley disulfide sample, which looks pretty nice, but immediately a trained eye of microscopist like Dmitry may notice some defects. If you process the image, do like this. Basically, you filter out some noise. If exactly the same image, you just basically use some software tricks to make vacancies more visible. You see that there are actually quite a few vacancies in the sample, these triangles. These are vacancies. And the question is, where does vacancies come from? Are these native defects which exist in your sample before you put it into TM chamber? Or these are artificially created defects by the electron beam? So, as a theorist, we try to give answer to this question. And in this slide, I'll give you some sort of crash course about how defects can be produced in transmission electron microscope. So the first channel is called ballistic knock-on edge. Let's assume the electron beam is coming from below. Normally it does the way around, but it doesn't matter. So electron goes through and it collides with one of the nuclei and kinetically transfers some momentum. It's like very high-speed bullet hitting a heavy ball. And then the atom can start moving. And now we can basically use density functional theory of molecular dynamics to describe the evolution of the system. In this case, you see formation of a vacancy and closed atom in graphene. So essentially, it's knock-on damage. You kick out atom from your system, basically ballistic. The second mechanism, Schroeck excitations. This mechanism works only in insulators and semiconductors. Again, electron goes through and you kick out electrons from your system. By the way, if your sample is not very well connected, electronically to the environment, you may get positive charge. Dmitry has a very nice demonstration of boron nitride tubes. So this is a bit counterintuitive. But remember that electrons have energies about 100 kilovolts. They go through atomically thin targets, and they also knock out secondary electrons. So, and this basically, this may or may not give rise to Coulombic explosion and production excitations and production of defects this way. The third channel is beam-induced etching. Vacuum is never perfect. You always have lots of jump in your chamber. Water molecules, oxygen molecules, and electrons, they break up the molecules, for example, create individual oxygen atoms, which are quite reactive, and they may etch your sample. You may ask me, is there any evidence that this mechanism really works? Knock-on damage is obvious, but as for other, recently my co-workers did very cute experiment, and they tried to explain that. They actually grew graphene from carbon-13. So this means that chemistry is exactly the same, but mass of each atom is different, it's heavier. So this means that electron kicks the atom. In normal graphene, if you're very close to the threshold, this means the minimum energy of the electrons when it starts knocking out atoms. In graphene 12, you will knock out atoms. In graphene 13, not. And exactly what you see in the experiments, if you basically plot number of missing atoms as a function of radiation dose or simply time. In graphene 13, nothing happens. In graphene 12, basically it loses atoms pretty quickly. Quality, fortunately, not. The projector is not very good here. You cannot see individual atoms. It's a bit dark, but still, I think you got the idea. Another important issue is that electrons not only knock out atoms. When you are close to the threshold, very interesting effects may happen. For example, in graphene, you may get a vacancy here, a constructed vacancy, but one atom is missing here. You can also get so-called stone whales defect. You rotate bond by 90 degrees. The electron comes from below once more. It's the movie. These are experiments, of course, with two images. And you see that the atom was almost displaced, but it came back, and you get two heptagons and two pentagons. So essentially, important issue here, electron beam can rotate the atom and give rise to topological defects. Basically, no atom is missing here in stone whales defect, but topology, local topology, is different. And this may also work in more complicated defects. This is divacancy. You take this bond, you rotate it, and you get a constellation of hexagonal rings, 5, 5, 7, 7 defects. Energy goes down, in fact. And essentially, these are all defects which my co-workers have seen in the experiments. For example, this is original divacancy is 5, 5, 5, 7, 7 defect. The next one, and so forth, and so on. And moreover, this way you can change the grain boundaries in graphene. Or even small grains can even completely annihilate. It's just an example of what electron beam does to your sample. Now let's go back to dichalcogenides. Again, a couple of years ago, our co-workers saw these vacancies and they asked us where these vacancies come from. To answer this question, we calculated formation energies of vacancies in different dichalcogenides, also calculated displacement thresholds. Once more, displacement threshold is the minimum energy, kinetic energy assigned to the atom, so it leaves the position and goes to infinity. If energy is not enough, it goes back, and then using binary collision formula, you can calculate the electron energy, basically simply two colliding balls, get the idea. what the electron energy was. So essentially the upshot is that in dichalcogenides only selenium or only sulfur is light enough to be displaced by like 80 kiloelectron volts, 80 kiloelectron volt beam, more or less standard voltage modern TEM works at. Selenium and tellurium atoms are way too heavy. Moreover, using the so-called McKinley-Feshbach formalism, you can calculate displacement rate as a function of electron energy and compare with the experiment. Basically, blue curve is for moly disulfide. This is the level calculations, and this is the experimental point, just clearly above the calculations. This means that in addition to knock-on damage, other channels work, basically ionization, electron beam-induced excitations, and possibly etching. It's still, for me, it's not clear actually what's the dominant mechanism is there. Here I would like to mention this basically slide is targeted at theorists only. Actually, it's a big challenge how to calculate charge defects in 2D system, because defects may acquire positive charge, local charge plane. And when electrostatics becomes a really pain in the neck in this case. The careful account for electrostatics effect. I'm not going to go into details here, just a side remark, but I can, basically, if someone's interested, we can discuss it after my talk. Okay, so these are typical defects which appear on the electron beam in microscope. These are results of our calculations, and based on calculations simulated TEM images that we compared them to the experiments. And more or less the same results were obtained by a number of other groups. This is the example coming from basically from the US, from Boris Jakobson, and they did calculations here. So nothing really spectacular, point defects, but interesting thing happens when you keep on your sample under electron beam. This is the movie. We keep moly disulfide sample under electron radiation. At some point, you see formation of some line structures. Basically like this, like that, or here another one, or there. And the question is what these structures are. Of course, the first aspect, vacancy lines, and we try to analyze the energetics when two vacancies meet and form line defects. For two structures, like single vacancy line or vacancies it can be on different sides, but in two cases the energy goes down, and based on our structure, if you can simulate the TEM images compared to experiments, these are exactly the structures experimentalists see in their TEM images. So basically, these structures can be explained through formation of vacancy lines. The more interesting question is the actual mechanism of transformation. If you take one slide from the movie, basically like that, and zoom it up, and 1 second later, you see that many vacancies in the upper part of the image, they collapse into line defects, while the vacancy in the lower part of the image, for example, vacancy this is still there, this vacancy is still here, so nothing happened in the lower part. And the question is, it happens pretty quickly, because recall that you cannot collect more than 10 frames per second with present-day microscopes, at least for moly disulfide samples. Otherwise, the noise to useful signal ratio will be too high. You will see essentially nothing there. So the question is how it happens. To answer this question, we calculated the diffusion barriers for vacancies. Diffusion does happen. For example, vacancy was here, now it moved to the next position, this way. But the barrier for diffusion is pretty high, about 2 eV, which means that at room temperature vacancies shouldn't move much, even with a count for electron beam effects. However, if you assume there is a vacancy already nearby, this atom is missing, and calculate the barrier, it will be much, much smaller than in the first case. This essentially means that the concentration of vacancies increases. At some point, the crystallinity becomes unstable with respect to pretty quick transformation to a lower energy configuration. And this actually very likely what, at least we believe, is what happens in experiments when concentration of electron beam-induced weaknesses increases. Okay, let's go back to Stonewall's defects. So in graphene, it's not very common defect, it's pretty high in energy, by the way. The concentration is negligible, but under the beam you can create that. Graphene has hexagonal symmetry, but other systems like boron-nitrine, Dmitry was talking about, and dichalcogenides, they have trigonal symmetry. So if you rotate two atoms, 90-degree transformation, you will have homoatomic bonds, which are not energetically favorable. Boron nitride, this will be nitrogen-nitrogen, boron-boron bond. However, you can do 60-degree rotation, something like that. Well, the density of atoms may be a bit too high here, but if you remove the atoms, the structure may be quite stable. In dichalcogenides, you should actually rotate like 6 atoms, like that. And in fact, if you look at TM images of tungsten diselenide, at some point you will find the signature of this very interesting trifolium-like defects. Basically, this is what, again, our co-workers found in several transition metal dichalcogenides. And basically, the structure is chalcogene deficient. Basically, 6 atoms are missing in this case, and then you can rotate this unit by 60 degrees. And actually, energy will go down as follows from our calculations. And in fact, you can consider this process, do more transformations, get another more complicated defects, and the process can be continued. What's interesting, it works nicely for, if you compare energetics of line defects and these rotational defects. Rotational defects will have lower energy in tungsten disulfide, tungsten diselenide, and moly diselenide, but not in moly disulfide. And exactly this is what experimentalists see in real life. In moly disulfide, they have line defects, while rotational defects appear in other materials. You continue the process, essentially you get a grain boundary, you actually basically phase here appears with mirror symmetry, and this have 5588 grain boundary, which by itself quite interesting. It's metallic and magnetic. Basically here you have like the CW grain inside bigger grain, and this grain was created by the electron beam here. Okay, so a little bit more about impurities and defects in moly disulfide. Basically impurities. This Dmitry, as I mentioned already, and Dmitry also touched upon, you may deliberately put something into your chamber, you create a vacancy, then defect, vacancy will be, then bonds will be passivated by some species which are in the chamber, because then bonds are really reactive, and this way you can dope moly disulfide with post-synthesis electron beam mediated doping. Depending what you put in there, you may get like donor acceptor states, so lots of freedom here. But again, experimentalists, as Dmitry mentioned already, specifically TM people, then you approach them with the suggestion to do that, they start hating you, because nobody wants to really spoil vacuum level in the TM chamber, especially in high resolution microscopy. But in principle, this works. Again, it's Dmitry demonstrated many times. And as this is definitely happens in reality. In this case, you see how vacancy disappeared, but difficult to say if it was another sulfur atom in moly disulfide or something else. Another approach is to grow doped materials. Here, the collaboration in this Tenzosurianides group, they characterized samples with rhenium impurities. According to our calculations, rhenium takes position at molybdenum atom, substitutional impurity, and also they had gold-doped moly disulfide. Gold seems to be on the surface, and in general it tends to make small clusters like here, and behavior is more complicated. As for electronic properties, rhenium has an extra electron, so it's obvious. Obviously, it's very nice n-type donor. It gives the new state, just field state, just very close to the conduction band minimum. With gold, situation is more complicated. But in general, when you get a small cluster, it's not our result. You may get a p-type doping contrary to rhenium, which basically gives rise to n-type doping. Impurities are quite reactive, it's well known, and this is exactly what happens when you have a rhenium impurity and molybdenum disulfide. Like formation of new carbon, nanocarbon, well, the small carbon clusters is stimulated by impurities in molybdenum disulfide. Again, this carbon is coming actually from hydrocarbon molecules present in the TEM chamber. So, to this end, doped molybdenum disulfide can be used for catalysis. Now, about mixing atoms. As we all know, graphene has no gap, boron nitride has a gap about 6 e. And the idea has been up in the air for quite some time to mix boron, nitrogen, carbon atoms and make a dream material with the value of the gap you want. Unfortunately, it doesn't work well because graphene and boron nitride tend to segregate. This is a cartoon showing basically small islands of boron nitride in graphene. Well, still, even though now I think there is a way to go around that if you grow these systems on like metals like ruthenium, which strongly interact with the growing layer. You may still get some sort of distribution, but it's still, I would say, not trivial and not obvious that the distribution will be homogeneous. However, we do know that in bulk ternary compounds, semiconductor, this approach works very, very nicely. You can very nicely. You can tune the gap depending on the constitution of the elements in your sample, concentration of the constituent elements in your sample. And some time ago, actually, we asked ourselves a question. Can the mix of atoms into 2D transition metal dichalcogenide? Will the system be stable? And what kind of properties you will have? For example, you can mix atoms in the chalcogen subplates like sulfur and selenium and molybdenum and tungsten. So this is what we did. In computer, it's pretty easy to do. You just mix up atoms. Again, recall that unit cell is more or less the same for molybdenum diselenide and molybdenum disulfide. And then we calculated free energy with a count for finite temperatures. Making a long story short, we found out that the mixed system should be thermodynamically stable at room temperature. So mixing should be possible. Then the next question is electronic properties. I'd like to remind you that bulk molybdenum disulfide has indirect gap, but single sheet is direct. And we use so-called effective band structure approach to calculate electronic properties of these random alloys. It's a bit counterintuitive because the system doesn't have periodicity, but what's important, the crystal structure is more or less the same. The differences in the changes in the unit cell size for mixed materials and for original materials is very, very small. So you can essentially calculate the electronic properties of a big supercell and then project it back to primitive cell and calculate the electronic band structure. The upshot is that the gap remains direct, and what's important, it can be tuned continuously depending on the composition, basically from 100% sulfur to 100% selenium, it will decrease. We published this in 2012, and I presented at several conferences these results, and experimentalists got interested in, and actually right now there are many groups which actually implemented this and proved our predictions. So to some extent, as a theorist, I am proud that not only we're able to predict something, but we also stimulated the research in a specific direction. Another paper just appeared, basically they control optical properties, and also we predicted that you can do the same trick by mixing atoms in the metal sublattice, for example, tungsten and molybdenum, and actually several groups did this. Again, tunable band gaps. Everything otherwise it's another paper. So finishing this story, defects can be useful in Dichalcogen or basically, I would say, this random alloys can be stable and used for engineering the properties. Now a little bit about more optical properties of Dichalcogenides and specifically molybdenum disulfide. I would like to, I guess everybody in the audience knows what excitons are. That remind you that when you create electron-hole pair, they in principle interact with each other. So the gap measured in optical experiments is smaller than the electronic or fundamental gap. It's just the same thing. It's just the issue of how you call it. And if you look at take standard approach, density functional theory with local and semi-local chain correlation functionals like LD or GG, and calculate the dependence of the direct and indirect gap as a function of separation between the layers. Basically, when we are here, this means you have isolated single sheet, and there you have a stacked material, and then you start increasing the separation between the layers. So essentially, you have a nice transition a bit from indirect to direct band gap, and as usual with conventional DFT, the gap is a bit smaller in the experiment, but overall agreement is fine. But it's also well known that you use GW approximation. It's some sort of post-DFT method to account for correlations and improve on the value of the gap you get. Strangely enough, you get the value of the gap and calculated as the function of separation in the layers, which is much larger than the experimental value, which actually gives rise to some confusion. Even some people question the validity of GW approximation for 2D materials. But in fact, the situation is pretty simple. If you calculate exciton binding energy by solving numerically the beta-salpeter equation, you will find that exciton binding energy also increases when you basically increase the separation between the layers. So this means that exciton binding energy is larger in 2D systems than in bulk materials. In bulk it's about 0.1 eV, in single layers about 1 eV. It's a very interesting effect, especially means that electron and hole wave functions, they overlap more in low-dimensional material. They basically are confined into a single layer. And then, if you look at the experiment, this brownish points here, and results of calculations. So once more, you first do standard DFT, on top of that you do GW calculations, there's a counterfactual spin-orbit coupling, and on top of this you solve beta-salpeter equation. You get a very nice agreement with the experiment here. Basically, this blue and yellow points. You can also account for the effects of environment, like more disulfide on graphene. So basically, this means that the gap depends on the environment. And recently, actually 1 month ago, was experimental confirmation of this effect. In that paper, they measured the fundamental gap using SEM in molybdiselenide on graphene, and essentially, effect is the same. Exciton binding energy is pretty large, much larger than the corresponding bulk system. So again, very nice information of, let's say, predictions. So theorists predict sometimes, or this prediction sometimes basically are correct, and even can direct research to new and create sort of new interesting areas for the research. You may have seen this slide from review by Gaia and Irina Grigorieva in Nature about staking the system up and making materials you want. And the question is how to simulate that if you want to do some theory. One issue is how to stack them, because the unit cell size may be different if you basically strain them to match, to have the same unit cell size. For supercell, it may give rise to artificial effects, but you can solve it still by constructing the right supercell size. But another important issue is the van der Waals interaction between the layers. Here I would like to remind you that standard density functional theory, this basically LDA or GGA circulation functionals, it doesn't account for van der Waals interaction. You should go beyond that, different levels of sophistication. And making the long story short, we did some very thorough tests, which approach is good, which approach is not so good, and calculate van der Waals energy for a large number of materials, which actually, and if you plot number of compounds as a function of typical van der Waals energy between the layers, pretty much all the values fall in the very narrow range, which means that van der Waals energy is, van der Waals interaction between layered materials is more or less universal. Whatever you have metals in a conductor, it's more or less in the very narrow range there. Okay, the final topic, I still have a couple of minutes, about two-dimensional silica, SiO2. This is a cartoon from 1932 paper by Zachary Eisen, where he wanted to illustrate the atomic structure of crystalline and amorphous silica. Normally it's basically glass. It's 3D system, but he just sketched 2D system because it's much easier to comprehend looking at 2D structure and then extrapolate to 3D. Interestingly enough, our co-workers looked a couple of years ago at graphene grown on copper, and surprisingly they saw graphene lattice with the unit cell size much larger than graphene was supposed to be in TM. And actually later on, from EOS analysis, we realized that it's not graphene, it's actually silica, SiO2 on graphene. And this is the top view, and this is the side view of the structure and perspective view. So essentially, you have a silica bilayer. So these are oxygen atoms, these are silicon atoms, this is graphene, and this structure can be crystalline. So it's small crystallized here as the grain boundary, or amorphous. And actually, this structure was obtained, in fact, accidentally, serendipitously. Some oxygen and silicon atoms ran from the quartz tube used for growing graphene on copper substrate, and this basically bisilica bilayer was grown between copper and graphene layer. Actually, I'll come back later on to this. Actually, in our calculations, I go back, we work out the most stable structure, and later on, as you know, in Russian there's expression to invent a bicycle, basically to do independently something what has been known before, but you were not aware about. We realized that actually the Berlin group, they grew up similar structures, epitaxial SiO2 and silica bilayers, van der Waals interaction on different metals for quite some time. In our case, copper was essentially dissolved and the structure was moved to TM green. So, together with Florian Banhart, we also looked at the structure of silica, epitaxial silica, and silica bilayer on different metals, which is a nice example of epitaxial silica, side view on, I think, on cobalt. And actually, the next slide here, just some animation, just to give you a better idea what the epitaxial silica, what you can see here, and this is just the same structure without the substrate. It's covalently bound to metal surface, interaction is pretty strong. and this structure doesn't exist without metal substrate like silicene, more or less. And this is silica bilayer, which is van der Waals bonded and it can be removed from metal. So why interesting? This, by the way, now is in the world, Guinness World Record book as a thinnest glass, but seriously speaking, it's very interesting support and challenge for microscopists, by the way. Besides, it's another paper coming from Silvano Lisi's group. I'm not, we're not involved into this work. They managed to intercalate silica between graphene and metal after growth. So essentially, this way you can isolate graphene from metal, at least electrically, without expensive transfer process. And also, you frequently create defects in graphene that you transfer it from basically metal substrate to polymers. And I believe that in our experiments with basically our coworkers did pretty much the same thing when they tried to grow graphene on copper. As I mentioned already, silica Si and O atoms, they ran from quartz tube and were intercalated between graphene and metal. Okay, and recently we looked at defects in these materials and graphene and SiO2, and what's interesting that the motifs of defects in these two diverse systems, recall that graphene is semi-metal, the silica is a wide gap insulator, but the symmetry is the same relative view, top view. So this is an example of stone wave defect in graphene and stone waves defect in SiO2. Also in the real time, microscopists can see transformations either way. Versus beautiful flower defect in graphene, essentially you rotate 6 bonds, one after another. The process can go either way, from pristine graphene to flower defect, or from flower defect to pristine graphene. All the atoms are there, you do not lose atoms. This example of flower defect in graphene, and the same works in SiO2. Actually, it's rotated by 90 degrees. If you rotate by 90 degrees, it's pretty much the same structure what you see here, but the scale is different. The energy for such formation energy of this defect is much lower in SiO2 because strain fields are compensated very efficiently for this defect. Dye vacancy, constructed dye vacancy I mentioned already today is butterfly defect, is the same, and I just rotated again by 90 degrees. And these are examples of in graphene and in SiO2. Also, the energetics of grain boundaries has something in common, even though it's still a bit questionable there. And finally, both silica bilayer and graphene can be amorphous. Amorphous graphene is something really special that you can make using electron beam under very special conditions. But anyway, it's like pretty much a random 2D structure, or almost random. There is still like short-range order in there. So lots in common between two systems. And as I promised already, just 1 minute. Recently, we just published quite, in my opinion, interesting papers about defects in one-dimensional system, truly one-dimensional. It's one-dimensional salt inside a nanotube which served as a container, and there some defects is possible. For example, cesium atoms can be missing or the other way around, and again, microscopists, our workers saw these defects, and we try to explain the experiments and also explain the electronic properties which material may have. And another example of one-dimensional ionic system, it's boron nitride chain made using a top-down approach, using electron beam. We just cut extra material. And what's interesting about one-dimensional chains of ionic materials, because metal chains, they have been observed, or carbon chains have been observed many times before, but these are two first observations of change in ionic materials, because ionic materials should be much less stable than the coordination number drops, I mean the number of neighbors for a given atom. But still they can exist even though under quite special conditions. So essentially that's all what I wanted to tell you today. Maybe just final remark that, thank you for your attention, and maybe just final remark that every year we have a workshop, a workshop at Finnish Lapland up north, and basically you are very welcome to attend this conference. So thank you once more for your attention.